Exercise 3.33. In each of the following cases, describe or draw a picture of the resulting quotient space. Assume that points are identified only with themselves unless they are explicitly said to be identified with other points. Part A. The disk with its boundary points identified with each other to form a single point. Let's just try to get a sense for what the answer might be visually before we write down it in many symbols. So the disk is just, we can take, say, the unit circle and the plane together with everything inside of it. I suppose I should color it in a little bit. Okay, so that's D, and it's just a set of all points x, y, in R2, such that x squared plus y squared is less than or equal to 1. Okay, now our goal is to identify all of the points in the boundary with each other. Okay, so and then we sort of end up on top of one another, but every other point just keeps to itself. So, well, here's how I imagine it. Let's sort of punch down the middle of this disk to make a bowl shape, so that the boundary circle ends up sort of up here, this is the top edge of the bowl, and then the rest of the disk bulges downward. All right. And then if we sort of keep going with that and start to draw together the top edge of the bowl and shrink it down a little bit, then we get maybe sort of a vase with a small opening at the top. Oh, that's not much of a picture, but you get the idea. And then you just keep going a little bit further, and eventually this top edge becomes a single point. And we are left with a sphere. Okay. Okay, so we think that probably this quotient space is just the sphere S2. All right, well, I suppose that's enough for what the problem said, but just to help you out a little bit, let me say what this has to do with, let's say, equivalence classes or quotient maps and partitions and all that stuff. So first of all, in terms of an equivalence relation, what is it here? All right, well, so we're taking points in this disk, and let's say some conditions under which a point AB in there would be equivalent to another point CD. It's going to be true if and only if, well, if the points are actually the same point, then they're certainly going to be equivalent to one another. So that would happen when A equals C and B equals D. Okay, but they're also going to be equivalent if they're both on the boundary circle, right? So we could represent that by writing, let's see, A squared plus B squared equals 1. So the first point's in the boundary circle, and also C squared plus D squared equals 1. Okay. So yeah, one equivalence class is the boundary, and then we have infinitely many equivalence classes on the inside. Every point by itself forms an equivalence class. All right, and then we could get a quotient map P from this disk D to the set of equivalence classes, D star. And, well, what's it going to do? It's going to map a point, most points AB are just going to get mapped to the singleton set consisting of that point all by itself, right? That's the equivalence class of that point, just itself. Okay, and that's going to happen if the point is on the interior of that disk. So if A squared plus B squared is less than 1, All right, but if a squared plus b squared equals 1, so that the point is on the boundary of this disk, then we're going to get the boundary as the equivalence class. Okay, and the easiest way to write that is just S1, meaning set of all points a, b such that a squared plus b squared equals 1. Okay, and that's going to happen for any point on the boundary. Okay, so here's the equivalence relation that we're talking about. Here's the quotient map, and then this d star, that is the partition. Okay. All right. So let's look at part C here. The interval from 0 to 4 is a subspace of the real numbers with integer points identified with one another. So what are we starting out with here? The closed interval from 0 to 4. There's 0, 1, 2, 3, 4. And we're identifying the integer points. So we've got 5 of those. Okay, so again, that's going to be one equivalence class, and then the other equivalence classes are just each of these individual numbers, which are not integers. All right, so we want to get those 5 points on top of each other without making anything else overlap, and so maybe we could sort of push down on these little segments in between the points and get something like this. So, well, that's a start. And then just imagine sort of bringing each of these points together on top of this point right here. You're going to get, well, a 4-leaf clover or something topologically equivalent to that. Okay, I've identified those 5 points all right here in the middle, and then no other point ends up on top of any other point, assuming that there's no overlap here. So this is the quotient space when we identify these integer points.